Okay, thank you very much. Let me, as I said, I'll introduce myself. I'm Ravi Mazumdar. I think most people at Links know me. I come like a spent penny all the time. Um, and so I'm a professor at the University of Waterloo. And what I'm going to talk about is a follow-up, really. It builds upon an earlier talk I gave last year at Links. And it's really a culmination of all those ideas uh, on real-time bidding in auctions. So I hope you will indulge me in the following sense, that the beginning part of the talk, I will go over with some of those ideas that I presented last year, um, just to put everything in context, because otherwise it doesn't make too much, it's very difficult to follow. And this work actually that I'm talking about forms the PhD thesis of my student Ryan Kinnear, who is going to defend roughly on the 11th of May. So he's right now in the midst of submitting his thesis. And this was joint work, of course, with Peter Marbach at the University of Toronto. And again, there is some history to this problem, is that this problem was posed to us by a company called Addictive Mobility in Toronto, which is what is called a demand side platform for placing ads, on mobile apps. And they posed the problem to us in the sense that they described their problem, and in fact they had no mathematical basis for how they were doing things. And they believed that looking at this problem from the point of view of trying to formulate the right mathematical problem would help really in automating their bidding and so on. So that's why I give special thanks to Addictive Mobility. And this funding was also supported by the Canada Research Council. Okay, so, oops, sorry. This is the mechanism of the problem we are trying to solve, right? So when you open a web page, a signal is sent to an ad exchange, okay? And there are two types of, so this ad exchange then contacts a so-called publisher of an ad and says that Ravi has logged onto this web page, and do you have any ads to place? So the publisher then has a list of potential advertisers, and they sort of bid, and sort of the person who wins the highest bid gets a chance to show the ad. So this is the context on which this problem arose. And the time scale, by the way, for all these actions, when we open a web page and an ad comes up, in one of these boxes, is about 100 milliseconds, right? So I will go a little bit more into ad auctions, and then I will say, well, what is the mathematical information you need for running a real-time bid? And I will give a suggestive model. It's not the exact model, but it's a suggestive model to think of why we're thinking in the right sense. And then I'll give you the notion of what are the issues being raised, and then talk about really the question of how to find these bids and what do we have to do in practice. Okay, so again, the real-time bid, you visit a website communicates with an ad exchange, and passes the information to people who might want to place ads, and the DSPs, or what are called demand side platforms, or it could be individuals, place ads, and the highest bidder wins the ad. And depending on the type of auction, whether it's a first price auction, in which case the highest bidder pays what they bid, or a second price auction in which the highest bidder wins but pays the second highest price, which is thing. Okay, and so this is really how you would have that. if you have these various bids, so the highest bidder would win, and which is say the second item, and they would pay the second highest price, which is $0.0039 to place the ad on that thing. And typically this this whole process takes about 100 milliseconds. And so what we need to do to try to understand this problem is try to formulate the problem with complete information. Okay, so what if you had all the information about the market? How would you really formulate the problem? And there are two basic approaches to a demand-side platform. What is a demand-side platform? Demand-side platform, I'm using this term without formally defining it, but a demand-side platform, you can say, is like an aggregator. He contacts various advertisers and says that I will place ads for you, and they sign a contract with an advertiser saying, okay, over this period in April, 3 weeks in April, we would like you to place 50,000 ads for us, and we would like these ads to be shown to people who open, say, apps for particular characteristics. For example, it could be restricted to a geographical region. It could be also including age, perhaps gender, and so on. So you could put a lot of criteria, and it's the role of the DSP or the aggregator to do this, purely because if you do it as an individual, it is less efficient. Okay, so that's why people go to these DSPs and they sign these contracts that I will pay you $5,000 for showing these ads 50,000 times to this targeted audience during this period. Okay, and the DSP then has to bid on these ad exchanges to try to show the ads of that advertiser to that targeted group. So there are two approaches really. One is to obtain impressions and then allocate them to the contracts they have signed. So I win something because I know this is part of the characteristics that many of my clients want, and I win it, and then I decide to which of those clients ads I will show. Or the other way is the DSP, if it has a small number of clients, can directly solve a problem of trying to place ads for that client. So that's really two approaches. And we will see that these are related to the structure of the primal dual problem that is associated with an optimization problem. And then the next step is, once we have done that, we have to try in this complete information setting to characterize the bidding prices and allocations. And once we have done this in the setting of trying to understand how to do this, we can then address the problem when complete information is unavailable. And then you have to develop algorithms to obtain or make bids and obtain impressions, obtain or fulfill contracts when the observations are censored, in the following sense that if it's a second price auction, you never know what's the price. You only know the price if you win, because you know then you pay the second highest price. Okay, so this is a censored observation. And the last part I will show is that really one can solve this whole problem through a stochastic approximation technique, but really one has to work a little bit hard because it's not a very direct technique. Okay, so this is the outline of the talk. So the first thing that we need to formulate this problem is something called the notion of a supply curve. So a supply curve, so consider a bidder who bids X for an item that becomes available in the auction. Okay, so a bidder is bidding to place an ad. A supply curve is nothing but a distribution function that characterizes the competing bidders. So and I'll tell you how it will come about, by giving a probability of winning an item given that you place the bid of X, right? So it's nothing but a probability distribution function, which so it maps, actually it should be R plus, so prices to some probability. And it just denotes the probability of winning an item with bid X. And for the sake of this talk, we will assume that it possesses a density. So in fact, it's continuous and derivative exists. But however, this assumption is strictly not necessary, but it's at the cost of more technical complications. And this we addressed in a paper at Sigmetrics in 2020 in our earlier work when we began thinking about the problem. Okay. So let me tell you how these supply curves arise. So let's take a very simple model. Suppose there are NT bidders and at time t, and a bidder is described by something called a bid and a rate. So the rate is R, so bid is the bidding price, and Rij is just the probability the bid will bid on item J. Okay, so bidder I will bid on item J, and the bid placed by I for items J are given by Bij. Okay, and so this is the state market. And suppose, since the winner of the auction is the one who presents the highest bid, then really what Wj will be instantaneously the maximum of all these bids. And then we can take and the maximum of bids. So if you have a market with n participants, you have these bid rates and so on, then the probability of winning when you bid X on an item of type J is given by an exact expression in this market, where I won't really specify all these terms. And so now if you look at a market in equilibrium, you can get an average bid price over the entire duration by looking at it really as the number in the market at any time given by an MG infinity process, because they come, let's assume they come. So these ads come as a Poisson process, and there is a certain time to place the bid. It could be 100, this is the 100 milliseconds, and you can actually compute this probability, average probability of winning. Okay, so now, once you have this probability of winning, you have the next part of the problem is this supply problem, is how these impressions arrive. And suppose they arrive at as let's say Poisson process for simplicity. So impression of type J arrives at rate lambda J. Then you get lambda J Wjx over to 0 to t. So lambda J Wjx, this is being the probability of winning. This is the rate at which they arrive. And so this is the rate at which you get these impressions of type J. And this is the number of impressions in an interval of length t. Okay, so it turns out that this probability of winning is what is going to play the role of the information state of the problem, which allows us to formulate the entire problem and solve it. Okay, so this is typically these curves that we measured on markets, which show that really they are probability distributions. So what happens is these are the bid values, and this is the number of impressions that you get for, say, this is one type of ad, which I call targeting group 2. This is targeting group 1, and you see both of them have this shape of a distribution function. Of course, this first curve is not that smooth, but we will assume that these curves are smooth just from the point of view of making life for us a little bit simple. Okay, are there any questions at this stage? Okay, so I'll continue. So now let us try to formulate the problem in the setting of interest to the DSP, or the demand side platform, which is placing the bids. So suppose there are M available item types, right? So there are 1 to M, and this we will refer to as the targeting criteria. So item type 1 could say be a particular region of Toronto addressing a population of age group between 40 and 50, and preferably, let's say, an Asian population, okay, and so on and so forth. So you have these targeting groups, and there's suppose M of them, and suppose the DSP has signed a contract with N different players. So each of these players, their campaigns could be satisfied by a number of these targeting type criteria, not just one of them. Okay. And so a campaign 1 and campaign 2 can share similar targeting criteria. And so there is an overlap of their targeting criteria. They need not be identical. And then the contract, which you say I, the ith contract has a duration of being active in a period 0 to ti. And this question of taking 0 as the origin doesn't change the real problem. Okay. And then we'll denote by AI the set of item types that can be allocated to contract I. So AI is the set of targeting criteria that can be used. So for example, if I'm saying I want an Asian of age 40 to 50 and preferably living in the eastern suburbs of Toronto, then it could be criteria 2, 10, and 11, right, of this targeting type. So it's a set of item types that can be allocated to contract I, and CI is the number of impressions required by the contract by the time TI. That means the DSP has to obtain at least CI impressions by time TI. Now, this is one formulation of the problem. There is another analogous formulation of such problem which has been studied, is that rather than give you a lower bound on the number of impressions required by a contract, sometimes people give you a fixed budget, and you have to get as many impressions that you can within the budget. But this is how the problem came to us. Okay, so this is the problem we thought which had a very nice solution. So let me ask the following question. If you had a formulation of a problem like this and you are a DSP, what is your goal? Your goal is to get CI impressions in the time 0 to TI at the lowest possible cost to you, because the difference between the contract that you signed and the cost to you is your profit. Okay, so you have that is sort of the motivation behind this formulation. So let me tell you.
Can I ask a question?
Yes, sure.
Yes. Is this CI a hard constraint? So I have absolutely to get CI impressions?
Yeah, I mean, you put it this way. These are all, because there is randomness involved, these are really on average. Okay.
Okay.
But you can put it in a hard constraint by modifying your formulation a little bit. Okay.
So in the contract there will be written, I mean, on average, you have to provide CI impressions.
Yes. Yes.
Okay.
And so this is how they will write the contract with you. Mm-hmm. Because they are also aware that not every time when you bid, you win.
Yeah.
Right? So the first thing we notice is that even though they are overlapping targets, there is a very nice decomposition. So let me think of A1, A2, and A3 are the targeting criteria for type 1, type 2, and type 3. Well, you see, you can break this down into non-overlapping targeting criteria BJ, such that if I belongs to BJ, then the corresponding J must belong to AI, targeting group, right? So these are in some sense, the Bs, the BJs are those targeting criteria that can be used to satisfy contract I, whereas J is the targeting group which is required for contract I. Okay, so you can do the split. And the advantage of this kind of split is that this problem, so you've taken an overlapping targeting criterion and converted it into a targeting criteria which are non-overlapping, and this makes the solving the problem much easier. Okay. So as a result of this, what we assume is that every item J is associated with the supply rate curve Wj, and lambda J Wjx is the average rate of if it arrives at the rate lambda J. And what is the rate of arrival of these? The rate of arrival of this is several thousands per second. Okay, so it's quite a high number. So lambda J Wjx is the average rate of winning items of type J. Okay, so I won't bother about these technical conditions. So now let's consider cost functions. Suppose there is a first price auction, right? And we bid X. So W of X is our probability. Then the average cost that you will pay is what you bid times the probability of winning. Okay. In a second price auction, you pay the second highest price. And so if you bid X, well, the second highest price can be anywhere distributed from 0 to X. So it is nothing but UWU, which is therefore, which integration by parts just gives you this quantity. And so you immediately see the cost of acquisition in second price auctions is always less than or equal to the cost of acquisition in first price auctions. Okay. I will talk a little bit of both, but my focus basically is on second price auctions. It turns out that the second price auctions is ideally suited to solve this problem, especially from the context where you have very little information from the market. So right now, this is a complete information context where we assume we know these curves W, right? And for each type, it will be Wj of X. So we assume we know these curves. But in reality, what happens is we don't know these curves Wj. So there are two approaches you can do. You know, a naive approach would be use part of your budget and part of the time to learn these curves Wj. And once you have learned them, use the Wj curves as if they are known and then start bidding on them. Okay, using that information. But we will see that that is strictly not necessary. You can bid while you learn. So we can do the problem formulation as this. So let Fjx of t be the price of acquiring a certain quantity lambda j Wj with a bid xij of t. Okay, so x of I is the, so I denotes the contract and j denotes the item type on which you're bidding. And gamma ij is the fraction of those allocated wins that you allocate. In other words, gamma ij times Wj should be greater than or Ci, because this is the fraction 1 of type J, and I allocate, or you can think of this as an allocation function, which I allocate to contract I from all the J's that are 1. Okay, and you have the natural constraints that the sum of all of this must be 1, and all of these must be non-negative. Okay, and you have to make the corresponding thing that because this is the time horizon 0 to ti for contract I, there are n contracts, you add it over all contracts, and we can modify these functions to be corresponding I, when it's indexed by I, those functions to be 0 outside 0 to ti. So this is a continuous time formulation of this problem, where you have the contract duration and you have a Fij function, which, if I go back, is either x wx times lambda or lambda times this quantity. Okay, So it's one of these functions. Okay, so now the key to this optimization is to understand what is called the cost of acquisition of these functions. So that means suppose I bid S and lambda is the rate of arrival. I look at Wj inverse of X, right? So remember, Wj of S is nothing but the probability of winning with bid S. So lambda j Wj of S is the average probability of winning those many items per unit time. So I look at this and apply it through this inverse mapping, and I call this function lambda j of X to be this acquisition function. So it is the average cost of acquiring a supply at the rate S of the item J. Okay. So in the second price case, you can show that this can be directly written in this form. And the most important thing is, since W is a distribution function, it's an increasing function. So it turns out that this function is convex. Okay. And what happens is, if you try to do it for the first price auction, you don't get such a simple expression. That is, you don't get convexity on the acquisition function unless you impose certain more conditions on the distribution function. And the distribution function must have something called alpha concavity. And so what happens is that in the first price auction, you get a kind of this function. Okay. So along with these functions, you can also define the convex conjugate, which is the Fenchel transform of with respect to these acquisition function. Let me call this lambda star. This we know, irrespective of whether this function is convex, as long as it's continuous, lower semi-continuous, this is a convex function. Okay. And we'll take this later on. So this is your formulation. You have these acquisition costs done over 0 to t. You need to meet these constraints, and the allocation, this should be small r. Rij must also, for all items so for all contracts for which item j is feasible, you should be able to, so Rij is the allocation vector of allocating this Sj to a contract I. Okay. So this above problem can also be rewritten in terms of these variables Rij by noting that you need this constraint to be satisfied. Then you can rewrite all these objective functions in terms of these functions Rij, and you can write an equality constraint for obtaining the number. And this problem has advantages which we will see a little later on. But there is something to notice. If I look at this equation of this equality constraint, the corresponding items here need not be full rank. Okay. That means what happens is that to satisfy a certain constraint, right, there may be more than one allocation, which will give rise to the same cost. Okay. So we'll come to that a little later on. So in order for this problem to have a solution, we need to have something called an adequate supply assumption, which basically says there is always enough ads coming around to satisfy your contracts. Okay, because if the number of ads that come are not sufficient to satisfy a contract, there is no way you can meet your contractual obligations. Okay, so this is just related to this thing. And so a simpler thing that says from 0 to tj, Wx, this is the the rate at which they arrive. There should be a lambda j over here, will always be greater than the total number that is required from all contracts for type J. Okay. And so one can also look at this dual through this Fenchel transform. And I'll tell you a little later on that one can, since everything is convex, we can look at the dual problem, and the dual problem can be solved in terms of these Lagrange multipliers. Rho I and mu jk is the dual variable. Okay. So now what happens is, suppose this mu and rho are the dual multipliers and related to the earlier problem, then one of the things one can show is that this mu j, which is the Lagrange multiplier, must belong to the subdifferential of this acquisition function gamma j. Okay. And more, one can show that if I look at defining mu j, this is the maximum over the quantities rho I. We can define a finite vector rho instead of an infinite dimensional rho over the end, because it's a continuous time problem, which will solve the problem with us. And so what you have is the following, that suppose I have these supply curves and they're in C1. And if you recall the second price auction, this was the form of the integral, and the first price auction was of this type. Then what happens is that the bidding price xj that I should bid to meet my contractual arrangements should be this quantity mu j in the second price case, and it's a little bit more complicated function in the first price case where this function gj is given by this, right? So it just thing. So this is a very key aspect of the problem. The fact that the second price auction, the derivative of the acquisition cost is nothing but W inverse of S. So W inverse of S, so S is the amount you bid and W of S is the probability of winning. So I look at the inverse probability of WS. This is exactly the acquisition cost. Okay. So there are two main consequences of duality. The problem says that the dual variables introduce subsets AI star, which are subsets of AI, and BJ star, which are subsets of those targeting sets that can satisfy a given contract, which have the effect of reducing the set of useful and usable items, in the sense that for an optimal allocation strategy R, if J does not belong to AI star, you will not allocate that to any contract. Okay. And secondly, the optimal bids, right, but not are obtained by mapping the dual solution through a bid mapping function Gj. And these bids can be characterized by these dual variables mu j associated with each item type through this vector, or indirectly we can also do it through these vectors called rho j, which I won't get into too much now. So some remark is the upshot of this calculation is in the second price case, the optimal path we know is actually constant between contract deadlines. That means if I have an interval Ti and Ti plus 1, right, between contract I and I plus 1, you can prove that the bid will not change during this interval. It only depends on the number of bidders present at a given time, and not really on the continuous time aspect of the problem. So it is enough in some sense to study the entire problem over one period. Okay. So far what we have done is we have shown that optimal bids can be obtained from dual variables associated with the optimization problem. This is of course contingent in knowing the acquisition functions gamma j that really depend on knowing the arrival rates lambda j and the distribution functions wj. So typically, you can get an estimate of lambda j because this is the rate at which these impressions arrive. Okay. But what you do not know or have information is information on wj, which is the distribution arising because other bidders are bidding on these items too. Okay. And this wj, which is the probability distribution, probability of winning, is something we don't know. So previously we assumed we knew it, and then we could know what is the structure of the bid, but we don't know wj. So in reality, we can only assume that bidders are independent. And second is in the second price auction case, we observe the prices only when we win. Okay. Okay. So like I said, one way is to assume that we use part of the budget to learn both lambda j and wj by constantly bidding very high so that you're guaranteed to win, right? And use part of your budget, win it perhaps at higher prices, learn about the curve wj and learn about lambda j, and then use that knowledge going forward. But this is really not necessary. And so what I'm going to talk next about is this question of how can we bid while learning. Okay. So since the problem of characterizing a correct bid xj given a desired supply is separable across j, right? Because we have decomposed those overlapping targeting sets ai into those non-overlapping sets bj. We will only assume that we consider a single type and therefore omit j from notation. And we'll assume that this is the lambda j. And let's assume that Poisson, so interval times tau n. And what we will assume is that w is not known. And we'll see that we can obtain by stochastic approximation. So for those of you who don't know what stochastic approximation theory really is all about, a stochastic algorithm of this type is said to be a stochastic approximation algorithm where this quantity mn plus 1 is what is called a martingale difference sequence. And this is called the gain of the stochastic approximation. And hn is typically the gradient of the function that you want to minimize. Okay. So the assumption is standard assumptions. This is Lipschitz, this is a martingale sequence. And this algorithm is said to satisfy Robbins-Monroe conditions if these ANs are, the summation of AN is infinite, but AN squared is summable. And then we have the following theorem, right? Just to tell you something. So suppose H is Lipschitz and the coefficients or the gains satisfies the Robin-Monroe condition. Suppose Mn is a square integrable martingale sequence. So what do we mean by martingale difference sequence? Mn plus 1 given Fn is equal to 0. And the second moment condition on Fn grows as 1 plus norm of xn squared. For some because I'm conditioned on I'm conditioning on xn. And then if you look at, so we have this function h, right? So this function h. So if I look at the ordinary differential equation dx by dt is equal to hx, if this equation has a unique globally asymptotic equilibrium point and the sequence xn is what is called stable, that means the soup of xn is finite almost surely, then you can show that this stochastic approximation sequence xn converges to x star, which is the unique equilibrium point of this differential equation. So this is what is called the ODE approach to convergence analysis. Okay, this theorem was first enunciated by Leonard Leung, and there's a very nice discussion of the entire theory in the book by Borger. For those of you who don't know this thing, okay. So it turns out to really solve this problem in the context of bidding, we also need a generalization of this stochastic approximation to what are called stochastic recursive inclusions. So what by inclusion, what I mean to say is that xn plus 1 belongs to xn belongs to this where H is now a set valued map. Okay, so this is the right hand side is a set valued thing. So it belongs to this. And what this means is really is that there is a stochastic approximation relationship being satisfied for some xn for some element h tilde n which belongs to this set valued map. Okay, and why do we need this extension is because you see we have functions which are convex, we don't know them explicitly, and so we need to take the subdifferentials, right? So we want and the space of subdifferentials forms these set value maps, and so we take an element from that subdifferential space and apply the stochastic approximation. Okay, so what happens is that if those conditions that I listed in the theorem for stochastic approximations, that you have stability and the martingale difference sequences are all, have those second order properties, then what you can actually show is that the stochastic inclusion will satisfy a stochastic differential, will be a differential inclusion. And then the goal is to say that if I look at this differential inclusion and my set valued map is concentrating, that means my set is decreasing, right, to a given point. That means there exists a point x star such that the set valued map, let's say, is 0 at that point. Then in fact, under condition what is called that if this H is a Marshall map, that means it's a convex compact, it maps convex compact sets into convex compact sets and so on, then you can show that the stochastic inclusion algorithm will also converge to that point x star. Okay, so this requires a little bit of work. So now let us look at 3 stochastic approximation algorithms. So first is just an estimate for 1 by lambda, because these are these inter-arrival times. The next algorithm is trying to estimate the function W. And the last is actually determining the derivative of lambda, or the acquisition cost. And we know that the derivative of the action cost is really W inverse, which is involved in getting the right bit. Okay. So
Ravi,
pardon?
I just have a question on the slide before, and in fact it was also in the previous slide. Mm-hmm. So there are some no, but go to the just this slide here. Yeah. Mm-hmm. With no, next slide. Sorry, I don't know. I'm lost here. It was about the condition about the AN. In fact, the sum should be infinite, and the sum of the square should be finite.
Yeah.
Is it important to have this condition?
Yes, it's very important.
You have some counterexample that doesn't work if you don't have these conditions.
You see what happens if so the summability condition really tells you that you have enough excitation. Okay.
This is what I understood at very high level.
And AN squared being finite really tells you that otherwise you cannot get convergence.
Okay.
Okay. So if you keep these ANs constant, right, you cannot prove convergence. Mm-hmm. But typically in practice, what people do is they keep these gains constant for a certain period because it gives you better adaptation. Yeah. And then they slowly vary it such that it meets these type of criteria.
Okay. Thanks.
Okay. So the remarkable thing is you can show that really, if you look at those three sequences, tau, x, and lambda n, they converge to the required rate function, and you get the converging to the W inverse of Sx by lambda, because this is what is the bid and this is the acquisition function. So these three functions converge. And yet, so, and then one can prove that really this, that if one looks at the ordinary differential equations defined by those stochastic approximations, then this point is the unique asymptotically stationary stable equilibrium. Okay. So what happens is that the above method gives a desired way that given a supply J, it estimates the cost of obtaining the supply as well as the bid Xj that attains this supply, right? That means for this Xj, you are really solving Wj inverse of Sj inverse lambda j, and both Sj and lambda j has been available. And so the thing that remains is to solve and calculate these allocations of the items Sj that you have won to the required contract. Okay. And one can do this. And what one can show is that you can have one algorithm which runs on the time scale for finding the bid. And once you find the bid, you can solve that allocation problem where these functions bt and gt are related to the fact that you have this equality constraint, right? You have summation rij times the thing equal to Sj, right? This is an allocation. So at every time you must allocate. And so these terms occur because what you try to do is at every time you try to impose this equality constraint by projecting onto the subspace of the of that equality constraint. And this is absolutely necessary, otherwise you get infeasible. So that means what you're doing is you're actually running a stochastic approximation on a subspace as opposed to the whole large space. And it's a 2 time scale algorithm because we choose these constants an and bn such that an by bn goes to 0 as n tends to infinity, right? So this is a fast time scale algorithm in which we get the optimal bids. And this is a slower time scale algorithm in which we allocate those bids to the required contracts. Okay. And so I will conclude my talk with showing you some results. So the first part of the talk to say is that, you know, this is an average case analysis. And if you want to really meet constraints, then you modify the capacity by a quantity 1 plus delta. This is from a practical standpoint, such that you try to aim for a larger quantity on average, and then you will hit your constraints. Okay, this is a very standard sort of trick that can be done. And this is how the stochastic approximation algorithms converge. So this is the first conversion for the inter-arrival time estimate, which is standard. This can be, you know, it's just 1 by n summation 1 to n tau I. So this converges very fast. And then you have the bid estimate, which is x, which is W inverse of S, which converges quite fast to the bid. And the acquisition cost estimate also converges. So it shows that these stochastic approximation algorithms converge, and this time scale is something very interesting to see. See, this time scale is of the order of 2000. What do we mean by 2000? It's not 2000 seconds. It's of the order of 2000 events, right? So in fact, you have convergence typically in order the moment you have 250 impressions that arrive, you have more or less converged on your bid estimates your acquisition cost estimates, and certainly the inter-arrival time estimate. Okay, and 200 events is quite good given that the arrival rates of these impressions is of the order of 10,000, right? Because it's related to the arrival rates of impressions on web pages. And this is the same thing. This is again, that once you get the supply rate, you want to allocate them, and so this is how you do the supply rate allocation of solving it at a lower time scale. So with that, I think I'm quickly running out of any goodwill that I would have. I will conclude, but basically, to solve the real-time bidding problem in both the first and second price case, we need this notion of a supply curve. And this problem has a very clear formulation in the original targeting, when the original targeting criteria is decomposed into the type targeting criteria with non-overlapping types. And the last part is really, we have been able to show that we don't need to spend time learning. We can bid and learn at the same time and still get convergence by using this stochastic approximation theory. So I think there is a lot more in this problem. For anybody who is interested, I will send you the PhD thesis of the student, in which all the details are really explained. So I've tried to give a very high level view of the problems. There are many important technical problems. So for example, like I said, if you want to solve summation Rij equal to Sj, right? So we want to allocate those quantities. This is an undefined system because the number of variables and the number of equations are very different, right? So you have more variables and you have the number of equations to solve there. And so what you have to do is you have to do some regularization, and the regularization really allows you to get a unique solution to this problem. And that, in that sense, that is related to, in some sense, proximal solution theory. Okay, so there's a lot of deep techniques that one has to make this whole theory practically implementable. Okay, with that, I'll stop and I'll give you some of the key references on which this talk is based. So the first paper that we wrote in 2020 formulated the problem for overlapping targeting criteria, where we did not make the assumptions that the supply curves were continuous. In the Sigmatrix paper of this year, we show a complete sort of link between the theory of supply curves and first and second price auctions and this duality theory. And the interesting thing is, one thing I did not mention, that if you do a first price auction and second price auction, numerically you will find that the bidding cost or the bids that you actually bid are not very different. Okay, and there is a reason for this. The only thing that matters in first and second price auctions, the highest bidder always wins. It's only what you pay that differs whether it's a first price or second price auction. And so the actual bids that you place are very close, whether it's a first price or second price auction. And therefore, what I feel is that even if you are bidding in an auction that is a first price auction, treat that auction as a second price auction and do this theory, and you will get the right bids. Okay. And then there was an earlier paper by Balsiero, Besbes, and Weintraub, which also tried to do this thing. But all these papers considered one targeting group, and they worked not so much with the supply curves, but they worked with utility functions for the bidders. And of course, the problem from a DSP's perspective is they don't know utility functions of thing, they only know costs. And so I believe our formulation that we have for this problem is a much more practical solution, because that is the problem that really a DSP faces, right? They don't know utilities of various people who are interested in bidding, but they know how much it costs them and they know the contracts. So one of the ways of this theory is that a DSP can use these algorithms, and that's what Addictive Mobility did. They used the algorithms on past data, right? And they saw roughly on a contract length of 2 weeks, how much it would cost them. And then when they signed contracts, they had an idea of how much it would cost them to get those many impressions. And that helped them negotiate the contract value. Okay. And then the theory of learning, in fact, is right now we are writing a very detailed paper on this. And if anyone is interested, I can share this paper with them. Okay, they're using the stochastic approximation and also the primal and the dual problem. So the primal problem is trying to find the bid. The dual problem is trying to find the bid and the allocations. And again, how the theory of stochastic approximation plays a role, and how the theory of stochastic inclusions plays a role. And it turns out that in this problem, all the nice conditions are satisfied and you can solve it. Okay, with that, I'll stop. Thank you very much.
Thank you a lot, Ravi. So, any questions?
Maybe I have two naive questions. Because maybe I didn't fully understand. I think so. So you assume that this W is sort of exogenous.
Yes.
Now, if all the players start to act as learners, so at the beginning they behave a bit chaotically, and then they converge to something. Maybe each one has a different learning strategy. I mean, is the theory still valid?
You see, there are many ways of explaining these W's, okay? So one is to think of this W as arising from a mean field setting, right? That means if there is one particular bidder who is learning, right, and all the other bidders are acting independently, then there will be an underlying distribution, except that the distribution we don't know, to which will be the fixed point of this whole procedure. Okay. So the mean field setting sort of motivates. So this is kind of the setting of mean field games and so on, where everybody is trying to do something. So they're trying to bid and everybody's bidding, right? And so if everybody is interacting in an environment, then really it will converge to some fixed point, and that fixed point is the distribution that you want, except you don't know it.
Okay. So this W is exactly this, is the result of the interaction. Yes,
the W is exactly the result of interactions.
Okay. And maybe another one, as naive as the first, is I would have expected that when you approach the deadline, this T, this upper T value, then strategy would change a bit, because if you have already collected a lot of, if you have won a lot, now you relax and bid a bit less. Or if you have not, you have to be paranoid, then you have to start to bid more in order to get your target.
Yes. It is absolutely true. You see, the right-hand constraint is CI, right? So if you look at the time formulation of the problem, at every time T, you try to get this bidding rate, which is CI of T. And CI of T could be C minus what you have already achieved.
Okay.
Right? So that's how it adapts. Okay. So as you get closer to the deadline, see, if you have not acquired too much, then the right-hand side is still large. And you have to allocate most of what you win to the given contract.
Yes,
so that's how it adapts. Right? So it's a little bit like a receding horizon control problem.
Mhm. Okay, thank you.
Other questions? So thanks again, Ravi, for your talk.
Yeah, thank you. And yeah, and hopefully I can come sometime soon and be in person in Paris. But, you know, I do
Okay.
not know. I think slowly, hopefully we are coming to the end of our pandemic, what I would call being averse to traveling and so on. But I think hopefully we are coming to that end. So hopefully when I come next time to Links, I can talk about something else.
Okay. Thanks. Thanks again.
Thank you. Thank you very much, and have a nice day, a remainder of the day. And here, I guess our day is still starting. Thank you very much.